The internet is a very powerful tool, putting the knowledge of humanity at our very fingertips. However, the internet is also a source of misinformation. You can hear all sorts of explanations, stated authoritatively and with good intentions, but also utterly and totally wrong. So in this video, I thought I'd address a common one and give a correct explanation for why light slows down in water. Actually, that's just a catchy title. I want to tell you why light slows down in any transparent medium, certainly water, but also glass, plastic, and even air. If you ever took a physics class, you learned about the index of refraction of a material. The index of refraction is just a fancy term for how much light slows down in that material. The index of refraction, always written as little n, is a number greater than 1. And the speed of light in a material is just the speed of light in a vacuum divided by the index of refraction. I put a table here to give you a sense of how much light can slow down in common materials. This slowing down is the reason that objects look bent when stuck in water. It's because the path that light follows bends when it enters or exits water. It's the reason that you can get pictures like this one here. And I should let you know that no physics teachers were harmed in shooting that photo. There's a ton of interesting phenomena I could show you that arises because of the index of refraction and the slowing of light, but I want to focus entirely on the slowing thing. So, to do that, let's look at this animation. So suppose you have a piece of glass with an index of refraction equal to 1.5. That means that light will travel at 2/3 the speed of light in the glass. If you shoot a laser at the glass, the light from the laser will travel at the speed of light until it hits the surface of the glass. When it hits the surface of the glass, the light will slow down to 2/3 its original speed, and it will change its direction. Once the light gets to the other side of the glass, it will emerge from the glass, change its direction, and move again at the speed of light. That's what happens. In addition, the light emerging from the glass will travel in exactly the same direction. Well, more precisely, in a path that is parallel to the direction of the incident light. The path is offset a smidge to the left, but the angles are the same. So that's what happens. It's been tested, and there's no debate on any of that. So now for the real question. Why does light slow down? And how can it speed up again when it leaves? There are two very common explanations that you find on the internet, and both of them are completely wrong. Let me tell you them first. The first one makes some kind of sense. It's wrong, remember, but it does make sense. It's the idea that light scatters off atoms as it passes through the glass. The light hits an atom and goes careening off at an angle, then hits another atom and careens off on a different angle. Light always travels at the speed of light between atoms. That process occurs again and again as the light passes through the glass, but let's focus on just these two scatters to see how the explanation goes. If we take away the atoms, we can see the important bits. There's the actual path traveled by the light in this scenario, which we can compare to the straight line path. If we straighten out the actual path, we see that it is longer than the straight line one. And if light travels at the speed of light in a vacuum between scatters, we see that it will take longer than it would if it went to straight line distance. Taking longer is another way of saying effectively going slower. And this is how some people explain the effective slower speed of light in glass. So how do we know it's wrong? Well, scattering isn't a precise process. Light can scatter in lots of directions. For instance, it could have scattered like we see here. This is a much more serious scatter with a much longer path, and consequently, light would effectively be much slower if this happened. Furthermore, there is no way to guarantee that the light would end up back traveling in the original direction. In fact, if light did what is being claimed, it wouldn't follow the path we observe. Instead, light would come out of glass with a range of velocities and a range of angles. This idea just doesn't work because it doesn't make correct predictions, so no good. The second wrong idea is that light is not scattered, but rather that it is absorbed and re-emitted by atoms. Between atoms, the light travels at the speed of light in a vacuum. The amount of time the atom takes to absorb and emit the light seems to slow the light down. You can see what I mean in this example here. The speed of the photons while moving is always the same, but the time taken during the absorption and emission makes the solid line take more time than the dashed one. This effectively makes light slower. Now, this idea, while sensible, is also wrong. Let's see why. The problem is that when an atom has been absorbed by a photon, it doesn't remember where the photon was coming from. And when it emits a photon, it can do in any direction. So what really would happen in the absorption and emission case is something more like this. The photon would be absorbed and re-emitted in a willy-nilly direction. In the end, the passage of light through the material would end up looking like this, which, well, isn't what we see. So, if neither of these ideas work, what does? First, I should say that these two ideas kind of have buried deep at the bottom of them the idea that light is a particle. However, the reason that light slows down in material is better illustrated if one embraces the idea of it being a wave. There are many properties of a wave, and most importantly, the wavelength. The wave oscillates up and down with a separation between peaks and a time between oscillations. A second important property is what we call superposition, which is just a fancy way to say that you can add them. And adding them is easy. You just take the height of the two waves and add them together. If the two waves are lined up so the peaks are at the same place, the result is a single wave with a higher peak. If the wave is lined up so a peak corresponds to a trough, then the two waves cancel. And if one wave has a different wavelength than the other, you end up with a funny looking shape. That's just how it works. It gets more interesting when one wave is moving at a different speed than the other one. The result is a different wave, but one that has a different speed than either of the two. That's super important, so let's just take a careful look at it. If we add the two top waves, which have different speeds, the bottom wave also moves, but slower. So let's get back to light moving through glass or water. Remember that light is a wave of electric fields. It oscillates with a characteristic wavelength and frequency. That wavelength depends on the color of light, with blue light being about 400 nanometers and red light being about 700. The numbers don't matter as much as that you remember that light is changing electric fields. Now, of course, glass is made of atoms, which are surrounded by electrons. Electrons have an electrical charge, and that charge feels a force from the oscillating field of light. Because it feels a force, the electrons move. But moving electric charges also set up their own oscillating electric field. Said simply, the oscillating electric field of light makes electrons move, which makes a second oscillating electric field. And if you have two oscillating electric fields, that's two oscillating waves, and you can add them together just like we saw before. The net effect is that the two waves combine and make a single wave of oscillating electric fields. And that is the wave that moves through matter. And this is important, it moves at a slower speed than light does in a vacuum. This also explains something that many people were confused by. Most people were willing to accept that passing through glass would slow down light, but they were very puzzled about light speeding up when it left the glass. That seemed like it created energy, and well, that didn't make any sense. But now I hope it does. Before light hits the glass, it travels at the speed of light in a vacuum. When it passes through the glass, the light causes the electrons to move and generate a second wave that adds to the light. Light still moves at the speed of light in a vacuum, but the wave from the electrons move at a different speed, and the combined wave moves slower than light would if the atoms weren't there. Then, when light leaves the glass, there are no atoms around to make electric fields to add to light, and then light speeds along at the preferred vacuum speed. So that's it. Light effectively travels slower through material because when it is in material, it generates a second wave that combines with the light, and the combined new wave moves slower than the familiar speed of light. Ta-da! All right, so tell everyone. This is something for which you often hear wrong explanations on the internet. But now you know, and that means you're eligible for membership in the Physics Cool Kids Club. Well, that was pretty awesome. I hope you remembered to like, subscribe, and share. I always love to find out the underlying answer for how things work, especially when you often find wrong explanations online. But, as is often true, the way to find out the right answer is to learn some physics because, well, as I'm sure you'll agree, physics is everything.